Hello, this is Dr. Amudapriya, Associate Professor, Triply, Rohini College of Engineering and Technology, Palpalam. We are discussing about the course Power System Operation and Control, and in this lecture we will be dealing with the static and dynamic analysis of the AVR loop. So let us first initiate with the static performance of an AVR loop. The AVR loop must regulate the terminal voltage to within the static accuracy limit, and it should have sufficient speed of response, and also it should be stable. The static accuracy requirement can be stated as for a constant reference input, likewise the constant error must be less than the specified percentage of the reference input. So let us consider the initial or the reference input is equal to 10 volts and the specified accuracy is 2%, then obviously the del error or change in error should be less than 0.2 volt. So this is the equation of the error formation, and while substituting the values we will be getting the transfer function as g of s divided by 1 plus g of s, which is nothing but the closed loop transfer function with the negative feedback, and substituting the value of initial value, so s is equal to 0 means we will obviously get this form of equation, del E0 is equal to 1 by k plus 1 into del V reference 0, where k is the open loop gain. Now actually this should be less than p is nothing but the percentage level, p by 100 into del V reference 0. So it can be concluded that the static error decreases with the increased loop gain. For a specified accuracy, the minimum gain is needed, and this obtained by substituting those two values. And obviously we can get when the static error is less than 2% of the reference input, the open loop gain should have reached greater than 49. Next, let us see about the dynamic response of the AVR loop. While considering the dynamic response, the equation of the del V of t is given by the inverse Laplace transform of del V reference of s into g of s by g of s plus 1. Mathematically, the time response depends upon the eigenvalues or closed loop poles, which are obtained from the characteristic equation, which is the denominator of the transfer function, closed loop transfer function, which is 1 plus g of s is equal to 0. The location of the eigenvalues in the s plane depends upon open loop gain and three time constants Ta, Te and Td0. Of these parameters, only the loop gain can be considered adjustable. It is interesting to show how the magnitude of this gain will affect the three eigenvalues in the s plane and thus the transient stability. Let us see about the root locus. So here we can see that we do have poles and then three poles in the x-axis, right? So they are at real part. I mean it is at the left hand side of the s plane. So the system is stable. Now the root locus, there will be three root locuses. One will start from this pole, s is equal to minus 1 by Ta. At this pole, the root locus will be starting and it will go for in search of the 0 to the minus infinity. While considering the pole at s is equal to minus 1 by Te, it is here, and that s is equal to minus 1 by Td0 dash is here. So what will happen is the root locus starts from this, it will move towards the right side, and from here, from the first one, it will move towards the left side. Both of them coincide at this point, and from where they used to start diverting away through the imaginary axis, they will cross the critical gain crossing and then it will go in search for the 0. So this is how the root locus is being designed here. So obviously we get g of s is equal to k divided by 1 plus sta into 1 plus stg into 1 plus std0 dash. There are three locuses as we have marked and their positions are being marked. The dominating eigenvalues S2 is thus small, resulting in a very slowly decaying exponential term, giving the loop an unacceptable sluggish response. So the gain k should be designed such that k is greater than 100 by p minus 1. thus rendering an inaccurate static response as well. By increasing the loop gain, the eigenvalue travels to the left and the loop response quickens. At certain gain setting, the eigenvalues S3 and S2 will collide and then go away. This is how we used to make the system, which actually these eigenvalue pairs will make the loop oscillatory with poor damping. So the AVR loop will now become unstable. So what we have to do is we have to bring the system to stability. Obviously, we have to choose a proper asymptotes, the direction of the asymptotes, I mean the angle of direction of the asymptotes should be properly designed in order to bring the system to stability, and this is how it is being given. Phi A is equal to 2L plus 1 into 180 degree divided by n minus m, where n is nothing but the number of poles and m is the number of zeros. Obviously, we will be getting this, that L value will be equal to 0, 1, 2, etc. So, we have obtained the 3 degrees, 60 degree, 180 degree and 300 degree, obviously. Thank you.